Recorder.
That's right.
Normally though, 10:30. It's my first class.
Let's start. Let's start.
Okay.
Yes, sure.
Wow. So this is cisp310, and let's see, how many people are also in 440? I just want to kind of get a rough estimate. I would say about maybe a fifth of people. Okay. So, so I'm going to start off the class with cracking a particular program. Okay, some of you have seen that already. I'm sorry that I'm going to do the same thing. But I want to give you guys, some reason to be interested in assembly language programming. Okay, and this is one of those. Okay, so I have a program that I have already downloaded. I demonstrated in the previous class. Is crack this 32-bit Linux program. There's a 64-bit version, which is going to use the same. It uses the same approach. It's just slightly different. Okay, so I'm going to work with the 32-bit version. And for people who have seen this before already, just try not to be too bored or fall asleep during the demonstration. And I might actually go a little bit further in this class because this is more relevant to assembly language programming. So let's go ahead and go to downloads. And the program is called hack132.script. Okay, the 32 is actually 32-bit because the other one is a 64-bit application. All right, so the first thing I'm going to do is just to run the program all by itself. It is a compiled program. It was written in C. Nothing really magical about it except that I made certain mistakes. Well, they're not mistakes. They're just I did not pay attention to certain things. Okay, so it works for the most part, but it does leave room for a security vulnerability. Okay, so there are ways to hack this program. So I'm running it right now. It's asking me to enter a password. Okay, so since I don't really know the password, I just give it some random stuff, and it comes back and say, hey, RTF DMCA, read the Fine Digital Millennium Copyright Act. Okay. For those of you who don't know what is the DMCA, go to Wikipedia, check it out, read everything about the DMCA. Okay. All right. So when I want to register, I want the program to see me as a legitimate user of this program that has full access to everything. Okay. So now I want to hack it, right? I want to see how I can trick this program to do just that. Okay. So the first thing people do, or the first thing that hackers would do, is to say, if there is a standard published, okay? So let's say the standard that is published is a password has to be up to 256 bytes, okay? What do you think a hacker is going to do? Break it, all right? What is the most important part of being a hacker? Is to think out of the box. Right? Where is the box? The specification, the standard. Okay? All of those documents that tells you what the program is supposed to do, those are the boxes. And the job of a hacker is to break the boxes. So if someone tells me the input is supposed to have 256 characters, what am I going to do? Give it more, right? How much more? I don't care. Just a whole lot more. Okay, so what I do is because this is a second class, I already have this pre-made, okay? So this is a text file that I'm going to redirect as the input. It has a whole bunch of random stuff, there's no particular pattern to this. I just kind of randomly bang out some stuff, from the keyboard, okay? And hopefully, nothing is actually repeating, okay? And I'm going to feed this as the input to the program, knowing for sure that this is more than 256 characters, because I want to break the box and see what the program is going to do when I give it something that is invalid. Okay. So a properly written program will just ignore this and say, hey, this is too many characters, I'm going to ignore it. But a improperly written program, written by someone who's lazy, who doesn't really think about all the possible cases, would make the assumption that everybody's going to play by the rules, okay? And those are the dangerous things that can make bad things happen. So what I'm going to do now is I'm going to run this program, okay, with the test in file that I have just shown you a little bit earlier, and the program broke, okay? Segmentation fault is the same thing as crashing, okay? Segmentation fault by itself is not a security risk. It simply means the program stopped working. It just crashes. Okay? But it does give me a flag and say, hey, maybe there is something I can do about this. In this form, there's not much I can do because all I can see is it crashed. So instead of just doing this, I'm going to do this in GDB. GDB is a debugger, and in this class in cisp310, we will all learn to love GDB.
Yay. The hard way.
Well, not using GDB is going to be even harder. So you will learn to like GDB. So I'm going to run the program in GDB with the redirection from test.in. Okay, so the program is going to crash exactly, the same way, but this time it gives me more information because it tells me one thing that is really odd. It tells me the program is crashing, and the location where it's crashing is in hexadecimal 4F 444554. Okay, don't you think those numbers are kind of special? If you look at each individual byte, okay, so I'm going to list these individual bytes on the whiteboard here. Okay, if you look at each individual byte, we have 4F, we have 44, 4F again, and then 5, 4. Okay, these are all in hexadecimal. So they seem to be kind of confined in a particular range, and the chances of that happening just by random is really small. Okay, so there has to be some kind of pattern here. When you see values within this range, they are valid ASCII codes. They are printable ASCII codes. They're printable characters. So now you go to the ASCII table and you find out what these characters are. Now, people from the previous class already know the answer to this question, okay? Because I intentionally put in TODO as the characters. So this is TODO. This is the ASCII code. 54 in hexadecimal is the ASCII code of uppercase T. 4F is uppercase O. 44 is uppercase D. Okay? Well, what did I just give it? I gave it a text file, right? So what I'm going to do is to say, hey, can I find this in the text file? The answer is yes. Some people may have noticed already when I showed you the text file. So test.in to-do TODO is right here. It is not ODOT. Okay, that will be explained later. Okay, because I just want to get you guys motivated to learn assembly language programming. So we will talk about little endian versus big endian later on. But it is in the file. Okay, so for some reason, okay, well, to us it is still unknown because this is something that you should know at the end of the semester, not at the beginning. Okay, so for some reason these 4 bytes, the content of these 4 bytes, help dictate how the program crashes. What do you think a hacker is going to think about this? What do you think a hacker is going to think of next based on this observation? I have some control, okay? I have some control over how this program is crashing. But I don't want the program to crash. I want to be authenticated as a proper user, okay? So that means if I know where to go in the program so that it will continue normal operation as if I have signed in correctly, that's how I want to hack these 4 locations. So that when I give the program this particular file as input, as the password, it will authenticate me and just go like, yep, you have full access to the program. Is that okay? So the way to do this is to locate that code first. Now to locate that code, okay, there are techniques to do that as well. So I'm going to quit this and look at a dump program. That would be good. Hexdump is going to work just fine. It's going to be helpful. So we can do a hexdump first. What is the name of the program? Hack1. Okay, there we go. Okay. Remember, we have some text messages coming out of this. Okay, this is not showing the ASCII code, so I have to do a -C. There we go. So on the left-hand side, we have the byte values in hexadecimal, but on the right-hand side, it will also display the printable characters. What do you think I'm looking for? To do? Well, I'm not looking for to do because this is not the actual input file. I'm looking for the message that confirms that I have access to the program or not having access to the program. So I'm just going to go through this. Oh, this is rather useful. Right there, welcome back, trusted user. Okay, that's a string, right? Okay, this is a clue. This is a clue because it gives me a location in the executable. And based on that location, if I can find code that gets this location, gets this address, that will give me the location of the part of the program that I want to hack into, that I want to jump into. Is that making any sense? And you can see the other message, your RTF DMCA is right next to this one. Okay? All right. So knowing that there's a message called welcome back, trusted user, okay? But I don't know when the program runs where it is. Right? So we have to find it. So we say gdb hack123 hack132.stripped. Okay? So now I have to find it. When I need to find this, I need to dump out the memory locations. So this is not going to work because it doesn't have anything like this. Okay, there's another tool called obj dump. And I cannot remember all the switches of obj dump, which is object dump. Now this is a utility program that can give you some insight of an object file, which include executables. So in this case, it can display a whole bunch of stuff. It can disassemble, it can show you the debug information, just information, section headers, line numbers, and source code and stuff like that. Those are not going to work because I intentionally stripped those extra data from this executable. I make sure that I do not have any way to cheat myself back into this program, so I can actually use the source code to find a way to defeat it. Okay, so I cannot use the -L or the -S because they are gone. Okay, but I can use the other one. I can use disassemble or the -D. Okay, so let's go ahead and give it a try. So obj dump -D hack. Okay, so let's go ahead and do a less here. Okay, so these are the instructions. Obviously, they make no sense whatsoever at this point. Okay, it's just a whole bunch of mumbo jumbo. But at the same time, we see something that is kind of interesting. Okay, see this label here, libc start main. What do you think that is related to? Remember, this program was written in C and C++. Program entry point. Exactly. Okay, so I'm getting some clue out of this. Okay, so there's a location of 8048350. I need to write it down. Okay. Oh, maybe I can just do this. Copy. Go back to the other one. Paste. Okay, there we go. Let's see if we can find anything also interesting. Okay, we find get s at blah 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 blah. Okay, if you take C and C++, you might remember a get s function. Okay, it's a function in standard C and C++. It's stdio. Okay, so that might be something that's interesting. Then we have more instructions like this. Get put. Okay. And then we have a .text section. Later on in this class, we will all realize the importance of .text. Okay, and look at the left-hand side. What do these numbers look like? Have we seen numbers like that before? Remember the start main label thing? What was it?
Memory addresses.
The memory addresses, and it ends with 350. So we'll go ahead and see what is at 350. Okay, looks like some sort of random instruction. There's a return right there. Okay, and there are some push instructions, some jump instructions. So now the question is, which part of the program is representing a part of the program that is past authentication? Well, you're not supposed to know, because you're going to learn all of these instructions so that you can actually read this. And then you can say, oh, I can disassemble this program and understand the actual flow of the logic of this program. Because once you know how to, crack this program and understand the flow of the logic, what can you do next? You can find out what the address is, right? So I'm just going to give you an example. This is probably not the case, okay? So I'll give you an example, and I'm going to say, well, we know there are some kind of conditional statements and whatnot, and these are conditional branches. So I'm going to give you an example, and I'll just say that at this point, the program has authenticated. Okay, this is the part of a conditional statement that is past authentication, past successful authentication. Is that okay? What do you notice? You notice the address 804837E in hexadecimal. So if I were to put these byte values into my test.in, then I probably can convince the program to jump to this location.
So like skip it.
Exactly. It's not returning back to where it's supposed to. It's returning directly to a point that I wanted to go to.
They can do that?
Oh, yeah. Absolutely.
It's like teleportation, right?
It's like, it's a hack to teleport yourself to a place that
to
you're not supposed
wherever
to.
you want in the world.
Exactly. Because you're messing around with the internal memory structure that we need to use for a normal program to execute. This is how hacking is done. Now, not simplistic like what we're seeing here, okay? But in terms of strategy, this is what is being done. When people hack, this is what they do. The first thing they do is they read specification, what is supposed to be the input to a particular program. Now it doesn't have to be standard in. It can be a file, can be a graphics file, can be a network protocol, can be a UDP, format for a game, okay? But anything that has a specification means somebody may not think carefully enough and make the wrong assumption that all packets coming in, all graphics files are properly formatted. So the first thing you do as a hacker is to break it, is to say, hey, this is supposed to be 32 bytes. I'm going to give it 64 bytes and see if the program crashes. If the program doesn't crash, make it even longer, because some programs, some programmers are lazy. So when the standard says 256 bytes, and they say, oh, somebody may try to break this program, I'll just allocate 1,000 bytes, 1 kilobytes, so that to mask the potential issue. Well, but 1,000 bytes is not enough, because if I give it something that's 2,000 bytes, it's going to break it. So what you do is you just try these different things to try to break the input to a program in various ways until it crashes. Once it crashes, you use GDB to find out how it crashed. And then you craft the input carefully, observe how it crashes, until you get a clue of what part of the input relates to how it crashes. And then you
that right there. So that text right there.
Yes,
crashed.
that is my first clue of how I might get control over this program, is the return address. Okay, now it's premature to talk about return address in the stack and stuff like that. But there's a concept called the return address, and it matches some content in the file. And that's the first clue that I might get some control over how this program behaves. And then I use this assembler. You have to understand these instructions. So hopefully this is motivating at least some of you to get through this semester without feeling that it's empty programming. Why am I in this class? Nobody seems to be particularly interested. Or are you just thinking that I might be working for the government? I am working for the government. What are you talking about? I teach at a community college. Of course I work for the government. Your taxpayer money is going into my pocket. Okay, but this is what we are trying to get to, so I'm hoping that this is giving you a little bit of motivation. Okay. Any questions about this? No. Yep.
Break the program?
Sorry?
Can we break it?
Go ahead. It's on Moodle.
No, can we, no, like, yeah, I mean, I'm definitely gonna try, but we can do it.
I don't want to do it now because I cannot explain, the instructions because we are quite a bit away from being able to understand the actual instructions. But once you understand, what these instructions are, what is a push, what is a sub, what is a call, what is a pop, what is a return, then you can actually analyze this code. Now, it will take you maybe half an hour, but you will be able to analyze what we are seeing here, figure out the exact landing spot that you want to end up at, craft those 4 bytes into the input file, and end up registering as an authenticated user. So remember this experiment, okay? So at the end of this semester, we'll come back to this one and actually break it. Yep.
So that text method, that is that return for that program, or is that the text?
It's a subroutine. It's the return address of a subroutine that got overwritten by the content of the file.
Okay, so it crashed and you got that.
That is my first clue of how I might be able to control the program
Okay.
by crafting stuff in the input of the program. Yep.
So that address there on the board, that's the address it crashed at in memory, but normally that address would be nowhere within like the normal range.
Correct. Yeah, that is way out of what it is supposed to be. Yep. All right. So now that we have a little bit more motivation, we'll go back to talk about the boring stuff again. And it is low-level mechanism and representation. We got started on this one. We talked about Moore's law. We look at this curve and see how things are improving exponentially. But we haven't really got to the point where we talk about the actual mechanism of what is a transistor. Well, a transistor or vacuum tube or relay or stuff like that is nothing more than a valve. Okay? Okay? It has an input, a control signal as an input, and it switches another thing either on or off. Okay? So think of it as a relay. Does everybody understand what is a relay in electrical sense? Sort of? Okay? So the thing about the relay is, unlike a regular switch when that you use your hand to kind of flip on and off, the thing about the relay is the output of the relay can be used to control another relay. And then the output of that other relay can also be used to control yet another relay, and so on. In other words, they can stack in a certain way. Okay? So that's the most important part about what a relay is. But there are 2 types of valves, okay, that makes it very convenient for computers to be implemented by transistors. From your perspective, you can look at these valves as positive versus negative valves. One type of valve will turn on when the input is high. The other type of valve will turn on when the input is low. That's basically what it is. Is that okay? And in actual relays, they also come in these 2 varieties. They're called NC versus NO relays. What is NO and NC? Normally open and normally closed. Okay, very good. So, right? Sorry? Did you say something?
I was saying what you were saying.
Okay, normally open, normally closed. But in terms of transistors, yep.
Does that have to do anything with logic gates?
Yes, eventually.
Oh.
We're getting to it. Okay, so I'm going to show you this little diagram here. Okay, so this diagram has 4 transistors. And I'm trying to find the best magnification so I can show the entire thing. There we go. So this is a circuit diagram with 2 inputs. T1, T2 are terminals for the input. T3 is a terminal for output. VCC is basically high voltage, and the little symbol at the bottom here, that's the ground symbol, which is basically 0 volt. Okay? So those are the quote-unquote terminals of this entire circuit. In the circuit, we have connections. So I want to point out the important part of the connections. If you see an actual dot where two lines meet, it means it is an actual connection. These lines are connected. If you do not see a dot like this junction here, it means one line is just flying over the other line. That's how most schematic diagram look like. Okay. So what we can see here is T1 as an input connects to this gate of transistor Q1, but T1 also connects to, let's see. Oh, T1 also connects to the input of Q3. Is that okay? So those are the only two transistors connected to T1 as an input. T2, on the other hand, connects to the input or the gate or the control signal of Q2. T2 also connects to the control signal of Q4. Is that okay? Okay. So remember the normally open, normally closed convention. One would turn on when it sees a high voltage, the other one would turn on when it sees a low voltage, right? As it turns out, in this case, Q1 and Q2 are the ones that turn on that will allow current to pass through when the input voltage is low. Okay? So when the input voltage is ground, they turn on. They let current through when that is the case. Q3 and Q4 are the opposite. When the input signal, or when the signal coming in from the left-hand side is high, they allow current to go through. When the voltage is low, then it is an open circuit. Is that okay? Sort of? All right. So I just want you guys to figure out all four possibilities. Because T1 can be high, T1 can be low, T2 can be high, T2 can be low, right? We are looking at high or low, okay? It's binary, it cannot be anywhere in between. So I want you to kind of think about what is going to happen to T3 when, for all four possible cases. And I am going to use my, not this one, I'm going to use this on the side to help keep track of that. There we go. All right. So let's get rid of all this stuff here. So we'll just go ahead, for no particular reason. This is the truth table. Let's say T1 is low, T2 is also low. And we'll go ahead and look at all four transistors, Q1, Q2, Q3, Q4. And then finally, we'll take a look at T3. All right. So if T1 is low, is transistor Q1 connecting or open? It's going to open because T1 and T2 are transistors that connect when the input is low. Okay? So we'll say it is it's closed. Okay, closing means it's connecting. So by the same token, Q2 is also closed. Is that making any sense? Because they're both the same type of transistor. They turn on or they make a connection between the top and the bottom pin when the input is low. Is that okay? All right. What about Q3 and Q4? They are the opposite type of transistors. They'll be open. Okay, so we put an O here, O and O. All right. So when you look at this picture in this configuration, it's basically saying that T3 now has two paths to find its way to VCC, which is the high voltage, right? Because remember, Q2 is closed, so it can go through T2 and connect to VCC. But Q1 is also closed, so T3 can now go through Q1 and find its way to VCC. But it has no way to connect to ground because Q3 is already disconnected. As if that is not enough, Q4 is also disconnected. So there's no way this pin, T3, can find any way to ground. So what do you think T3 is going to measure in this case, high or low? It's going to measure, VCC is high, VCC is 1. We have two ways to get to 1. So the output is going to be a high voltage, a 1. Is that okay? Sort of? Okay. All right, let's look at the next one. Let's say T1 is still a 0, T2 is now a 1. So in this case, Q1, remember Q1 is this transistor, it is connected to T1. Because T1 is still a low signal, Q1 will still be connecting. Q2, on the other hand, will now be open. What about Q3? Q3 is connecting to T1, and this is the one that turns on when the input is high. But since the input is low, is it open or closed? It's going to be open. Okay, T4 is the one that is going to be closed because T4, okay, if you look at the schematic, T4 or the gate or the control signal of T4 goes to T2. But remember, Q4 is the kind that turns on when the input signal is high. And T2 is high in this case because the truth table says T2 is high in this case. So that means Q4 is connected. It's not open. Okay. So now that we know the configuration of all the switches, what about T3? There is a way for T3 to go to VCC, right? Through which transistor? Q1. Yeah, Q1 is still connecting. Okay, now Q1 and Q2 are parallel. Only one is needed for T3 to find its way to VCC. So we certainly have a way to go to the high signal. But we also have to make sure there's no way to go to the low signal. Because if you have a connection to both to the high and the low signal, then you're going to be looking at an exploding chip. Okay, bad scenario. So can we find a way to go to ground, to go to the low signal? Now Q3 and Q4 are connected in series, which means if one is open, the entire circuit is open. So between Q3 and Q4 is at least one of them open. Yep, at least one is open, so there's no way to go to ground. So now I can, confidently say that it is still high. Right? T3 as a terminal will still be measuring a high voltage. Is that okay? Does everybody kind of see how I figure out these numbers? Okay. The next one is having T1 being a 1, T2 being a 0. Now, if you look at the configuration, for the most part, they are symmetric, right? So without going, well, I guess we'll go through this. T1 is high, Q1 is going to be open. T2 is low, so Q2 is going to connect. And T1 is high, so Q3 is going to connect, and Q4 is going to open. Okay? We're basically just alternating the on-off switch. Okay? In this case, because I only need one way to get to VCC, and in this case, Q2 is the one connecting to VCC. So T3 is still connected to VCC as a result. But nothing is connecting nothing is connecting T3 to ground because between Q3 and Q4, they both have to be connecting in order for me to connect to ground. And in this case, Q4 is the one that is open. I do not have a path to get to ground. So that means the output signal would still be a 1. And I don't think I really need to explain this one because we have been looking at ones all this time. Okay, so let's take a look at this one. This is the last one. Q1 and Q2 are both transistors that will open when the input is high. In this case, T1 and T2 are both high, which means Q1 and Q2 are both open. Okay, they're not connecting anything to VCC. Q3 and Q4 are both the types to turn on when the input signal is high. In this case, on this row, T1 and T2 are both high. So that means Q3 is connecting, Q4 is also connecting. Now Q3 and Q4 are in series. When they are both connecting, then we have a path from T3, terminal T3 to ground. Ground is 0. So that means T3 is going to be a 0. Okay. Are there any questions about this picture? This schematic? questions? Is there anything interesting about this picture? Other than, oh yeah, but the transistors, when this one is on, that one is not connecting, and we can determine the output, which is T3, from the state of the inputs, which is T1 and T2. Anything significant about this? But let me clean this up and see if you can find something that is remotely interesting. Yep.
It resembles true and false for OR.
Okay, so I'm going to relabel this x, y, okay? And this is x something, something, y, some kind of operator. I don't know exactly which one it is, but I'm just going to say it's some kind of Boolean operator. So 0, 0 gives me an output of 1. 0, 1 gives me an output of 1. 1, 0 gives me an output of 1 again. 1, 1 gives me an output of 0. Okay, so you think about all the normal logical operators that you know, and you go like, comes close, but not exactly, right? Because if you think about OR, this seems to be exactly the reverse. Well, okay, it's kind of like the reverse of OR. If you think about AND, it's not quite AND either. Because if you have AND, then the first 3 rows should be zeros, and the last one should be a 1.
We are opposite.
Oh, hold on a second here. What did I just say? The first 3 should be 0, and the last one should be a 1, which is exactly opposite to what we are seeing. In other words, this is the inverted version of AND. Does that make any sense? NAND. It's called NAND, N-A-N-D. Okay? So here we have N-A-N-D. But if you don't like the word NAND, which is not really a word, your English professor will definitely not like that when you say negated and is that. Well, you can always write it like this, right? It's the negation of the conjunction. Well, no one seems to be excited about this. And you guys are all on your way to get your computer science transfer degree. Okay, first of all, why should we be excited about this? It's just random transistor circuit and some truth table. Well,
Because this is pretty much a circuit that illustrates code.
logic gates.
Logic gates. So
Right.
That's what I was saying earlier.
So we are making an association between a math programming concept and actual physical
real
stuff, right?
stuff,
Transistors, traces, wires, and voltages, right? Yep.
If the circuit is the motherboard or part of the motherboard, that's how the data is written on the outside. That makes sense.
Well, not quite, because a hard drive is a magnetic medium, so it's not really quite the same. But there is association, okay? What we have here in the circuit diagram is physical, okay? We are looking at 4 actual transistors, wires, conductors between the terminals and stuff like that, high voltage, low voltage, and stuff like that. It's all physical. It can be implemented. It can be done, right, in the physical world. But when we are looking at the truth table, we are looking at a familiar concept that is just logical. It's mathematical, it's programming, and stuff like that. It's the implementation that is interesting. This is one way to implement the negation of a conjunction. Yep.
And also, you can use NAND gates for pretty much all the logical. There's cheaper and standard.
Yep. Well, it depends on the substrate, because when you're manufacturing semiconductor, your substrate is a particular type. It usually is an N type. So when your substrate is an N type, it is cheaper to make a certain type of gate as opposed to the other. Yes. Okay. So now that we have this thing, which is really, I think it's pretty exciting because we have a circuit that can implement a logical operation. And then somebody's going to say, well, but who's going to use NAND? I have never encountered this word NAND until today. Who is going to use that? Well, the next question is, can we get back to the normal Boolean operators from NAND? Just NAND all by itself. Think about it. Okay, let's think about this a little bit. What type of logical operators do we usually use in programming? We use negation, right? Yep, go ahead.
What if you swap the positive with the negative?
What do you mean by swapping the...
So VCC becomes ground.
It doesn't work because that's not how the transistors
It'll
work.
just burn up.
Yeah. In fact, yes, it will just burn up because these things have an internal diode, which means the current can only go one way.
Flows one way, yeah.
So if you flip VCC and ground, the diodes will be in the what we call the forward bias configuration. So they would just be dumped. You would just be dumping current from one end of the transistor to the other end, and these things would just burn up. Not that you should try that, but I think that's what's going to happen. Okay, so let's talk about NOT. Okay, just the normal negation gate. Okay, if all I give you is NAND, can you implement regular logic negation using NAND? Okay, so I want NOT X. Okay, this is what I want, but I only give you NAND. How do we do this?
Not NAND.
No, we cannot use NOT on the other side. We can only use NAND on the other side. So how do we only use NAND to implement NOT? What about this? Would that work? Doesn't seem like it's going to work. Wait, I want to look at AND all by itself, not as NAND, and put the negation back on the outside. Let's see whether it works, whether it looks better that way. Okay. So we'll say, well, does it actually is it the same thing as a negation of X and X? What is X and X?
So we're saying that not X and X are the same thing.
Okay, so wait. Let's simplify a Boolean expression. What is X and X?
Both have to be true for the.
Oh, come on, guys.
Whatever X is, X.
Truth table. We got
It's
X.
true, it's true.
Okay, we only have one variable. What can it be? It's a Boolean. What can it be?
True.
True or false? 0 or 1. Okay, fine. 0 or 1. Right? If X is 0, what is X and X?
The one has to be 0.
0, right? Because 0 and 0 is 0. What about what if X is 1? What is 1 and 1? It's a 1. Oh, so X is the same thing as X and X.
Yes.
Okay? So that means that equality actually holds. Not X is really the same thing as X and X. In other words, using just configurations of transistors like this, I now have a negation. I have logical negation by itself. Is that making any sense? Sort of? Yep.
So is not X and X, is that saying, so for it to be true, X and X have to be there, but not means that they don't have to be there?
I'm just rewriting NAND, right? Because the original thing is if this is the only configuration, but you can have any number of these things, can I implement the normal Boolean operators? That's the question. So one of the normal operators in Boolean is just normal negation, just not X. So the question is, if I just give you NAND, can we get just negation? That's the question. And the answer is yes, we can do it because we can just say X, NAND X is the same thing. In other words, if negation is what you want, then you connect both T1 and T2 to the same signal. And then the output is going to be the negation of that signal. Is that okay? It is kind of a waste of 4 transistors, but it can be done. Is that okay? Okay. So now that we have negation taken care of, let's look at just regular AND. So can we deal with x and y using NAND?
So it would be like not x and y, same thing.
Well, okay. So we can say, what is x NAND y is not quite enough to do that because that's the negation of what we want, right?
Says NAND X
Oh.
or Y.
X NAND Y, NAND X NAND Y.
Yes, very good. I'm glad that you can say that without making a knot of your tongue.
But why?
That's it.
Would you ever want to do that?
Well, just so that we can do it. Because what we want to do is to say that, this circuit is enough to implement everything that we need
Okay.
to implement. That's all I want to show. Okay. Whether it's efficient or not, that's besides the point. That's for Intel to figure out. Right? Okay. So NAND and is okay. What about OR? Oh, that one is nasty. What is OR? Well, this is the time where where Mr. De Morgan is going to come in and say, "Well, I can help you solve this problem." Okay, what is De Morgan's law? Okay, so let's take a look at De Morgan's law first. Okay, D is lowercase d. Morgan's law. Okay, De Morgan's law is really cool because this allows you to relate conjunction to disjunction through negation. Okay, I know that sentence or that statement sounds really, really odd, so I'm going to show you exactly what it is. The negation of x and y is the same thing as not x or not y. You can kind of look at this as distributive law, but you're distributing the negation. But not only are you just distributing the negation, you have to change the operator. You have to change the and to a or. But it also works the other way. Okay, the other way is this: not x or y is the same thing as not x and not y. It works the other way as well. Okay? Do you trust me? When I say something is true, do you say, yeah, text says that it has to be true? Well, if you're new to my classes, I'm not going to blame you, but if you're taking classes from me, this is when you will say, I'm not so sure about that. Right? So how do we prove this? How do we prove De Morgan's law?
Truth table.
Truth table, very good. Simple, right? Truth table. Because with each De Morgan's law, we only have 2 variables, which means we end up with 4 rows in the truth table. Figure out the 4 combinations of x and y. 0, 0, 0, 1, 1, 0, and 1, 1. Figure out what is the value of this expression. Figure out what is the value of the other expression. If on all 4 rows they are exactly the same, then the 2 expressions are equivalent. They are exactly the same. That is why Boolean algebra is so cool, because you don't have to prove anything using actual proof. You can enumerate all the possible cases. If 2 expressions come up with exactly the same results, then they are equivalent. It's easy to prove equivalence in Boolean algebra. Okay, so I'm going to leave it up to you guys to prove this. Okay, so you can just go ahead and use your little spreadsheet or whatever to prove this. But this is De Morgan's law. I still don't get it. How does De Morgan's law help us? What do you think? Okay, so we have De Morgan's law, but we also have double negation, right? Is that okay? So does that seem okay to you? Double negation is doing nothing. Good. So I will leave one negation, but re-express the other one. So the outer negation, I'm going to keep it. But the inner negation, I will apply De Morgan's law. So when you apply De Morgan's law, what do you get? It becomes not x and not y. Is that okay? That's just the application of the Organ's law to the negation of x or y. Okay or not? Okay. So if this is okay, then we still say, well, that doesn't look like NAND to me. Well, I can see one NAND already, immediately. Because there's a negation on the outside and a conjunction in the inside, right next to each other. So that combines into a single NAND. Okay, so that's good. So we got one NAND solved already. Because this whole thing becomes just not X, NAND, not Y. Oh, but earlier we already know how to do negation using NAND. It's just using the same variable on both sides of the NAND. It becomes just regular negation. So now we can just say that this whole thing really is X, NAND, Y, NAND, Y. I have just re-expressed this junction, which is 4, in multiple NANDs, multiple negation of conjunction. Is that okay so far? And what is the big deal of this? Now remember, we went from transistors to a seldom used logic gate called a NAND. Okay, that's the first step. And I think that step is really important because we can now use physical devices, relays, transistors, vacuum tubes, air valves if you want, mechanical devices, as long as you can have one normally open and one normally closed structure, this will still work. Okay? So we can use physical, actual devices, mechanical or electrical or otherwise, to implement a logical function, which is kind of odd. It is called the negation of conjunction. That's the first step. This is the second step. From that really odd negation of a conjunction, we now have a way to implement every logical operator that we are used to. The details is a little bit daunting, a little boring, a little dry, but the important part is we can do it. We can use transistors to do negation, to do conjunction, to do disjunction. Is that okay? So that means most, if not all, of the Boolean stuff that we do can now be done using transistors. Good? Okay. So now I think that is almost the end of this slide. Not quite. We'll keep moving a little bit. This is just re-explaining what I just talked about, but using pictures. So in a picture like this, I just want to show you the picture. Okay, in a picture like this, this is a NAND gate. Okay, because by itself, this symbol is an AND. This little bubble here means negation of the output. So the negation of an AND is a NAND. So this is how we do just regular negation. This is how we do disjunction, and this is how we do conjunction. Okay, just re-expressing our formula into gate representation. Is that okay? All right. So I'm going to skip a little bit about analog versus digital stuff, because all computers these days are not just digital; they are binary. In other words, we represent everything using zeros and ones. So this is getting back to how many samurais do we see? 7 samurais. Okay. In fact, I think the anime is called Samurai 7. Okay, it's a pretty cool, anime, Japanese anime. So 7 samurais. Okay. The quantity that we want to express is 7. There are 7 people in this picture. Okay? But what is 7? S-E-V-E-N. It's a representation of a quantity. Okay? When you write it out as a number, what is 7? What represents the quantity of 7 when you use a number to do it? Okay? You guys will be thinking like, Tech is out of his mind, he's asking us how to write 7.
Is it base 10 number?
Okay, that is 7. But you know what? If you ask me, 7 is 111 in base 2. What about base 5? What is 7? The quantity is 7 in base 5.
52.
What about base 4? 3. What about base 6? Yeah, exactly. So this means there are multiple numbers, multiple representations for exactly the same quantity, the same value that we want to represent. Is that okay? If you don't want to see it like this because you don't like to deal with different bases, think about it like this. Does everybody in this world use US currency? Okay. I was hoping that nobody said yes, but so that's good. Okay. So you guys are all aware of other countries use this around. Okay, so there are other currencies, right? There's the GE, Great Britain pound, euro, renminbi, in China, yen in Japanese, and so on and so forth. Okay. So when you look at the price of a bottle of Coca-Cola, okay, how much is it in the U.S.? Okay, let's just say it's $1. Okay, $1, okay. But in other countries, the same worth can be expressed by other currencies. So that it's the same thing, okay? It's not base conversion, but it's currency conversion. So you're talking about how much something is worth, but you can measure that in different units. And that's kind of what we're dealing with here. Is that okay? Because I want to make sure that we separate representation from what it is actually representing, the actual thing that it is representing. Well, what is this face? It's a happy face, okay? There's no trick in that question. Unfortunately, I don't have any font installed here, except for, well, I do have some, okay, that's good. So in Russian, it's this. I do not speak or understand Russian at all. I did Google Translate. Okay, so that's Russian for happy. Is that right? I mean, does anyone know Russian?
I do, but it's really tiny.
It's really tiny. Okay.
And I really assimilated to this culture, so yeah.
So no.
Well, the last word is.
All right.
That's a weird thing.
Okay, I will do the other thing. I'm going to go back to Google Translate.
Maybe it's trying to say счастливый, and what that means is like uplifting emotions.
That's the inverse function.
The thing is, Google Translate is not good.
Well, it's better than me.
Some things don't quite translate.
Are you saying they don't have a word for happy in Russian? Because I think I might translate.
Oh, that is so
that word doesn't
political.
look happy.
That word may not exist in Klingon, though.
I'm sure it doesn't.
Let's see if Google Translate can do Klingon.
You know it can.
There's no way.
Okay, where's K? K, Klingon.
You know, when you're going from
Oh, it doesn't have Klingon.
What?
when you're going from language to language and you keep going back and forth like that, it'll like totally change it into a different word. By the time you get back to English, I've done that.
Oh, okay, well.
Linguistic telephone.
Yes, that's what it is.
Vietnamese, does anyone know Vietnamese well enough to see whether that is happy? Or close?
It's close.
Maybe close? Okay. I think that's Spanish. Is that happy? I recognize that. I mean, Happy New Year. I know that word is Happy New Year, okay? All right, so the bottom line is, this is the emotion that I want to represent. These are symbols, these are words to represent that so that we can communicate. So numbers are exactly the same way, because if I ask you, what is your GPA, okay? Well, you have to use numbers to represent your GPA, okay? It's a quantity, it's a value, but you have to pick a representation that both you and I can understand to convey the concept of that particular value. Is that making any sense? We are looking at exactly the same thing here. Base 10 is base 10 because we got 10 fingers. Well, the computer doesn't have 10 fingers. Transistors don't have 10 fingers. What do transistors do? On and off, 2 states. And that's why 111 in base 2 is much more native to computers than 7 as a base 10 number. Okay. Are there any questions about numbers which are representations of values? Are there any questions about that? Questions? Okay. So if there are no questions, I think we are pretty close to the end of this slide. Oh, base conversion is easy, because it really is easy. If any one of you has the opportunity to work at, let's say, McDonald's, okay?
Opportunity. I
This
aspire to
is
such greatness.
opportunity to work at McDonald's, and I have to go back to my sponsor.
Peter.
And you have to figure out how to make change for, let's say, $2.75. So $2.78. Okay, let's make it really hard. Can you do it? $2.78. How many people would just count 278 pennies? Well, that's one way to do it. What if I tell you you have to use the least number of common bills and coins to make up this particular value? So $2 bills are out of the question because they are not common. Okay, so how do you do this? You start with the biggest one that is applicable, which is a dollar bill in this case, right? So in this case, you start with a dollar bill and say, oh, we need 2 of those. Once you take care of the $2, you have 78 cents left. So the next most common denomination is a quarter, 25 cents. So then you say, oh, okay, we'll take care of the quarters, and we can have 3 quarters, which takes care of 75 cents, so now you have 3 cents left. Then you move on to, well, dime doesn't apply, right? Nickels do not apply, so you move all the way down to pennies, and you say, okay, we'll look at pennies, and we'll need 3 of those as well. This is a lot harder than base conversion. Do we have any regularity in terms of these denominations? A penny? Okay, let's take a look. Okay, most of you guys do not even think about this because you're so used to it. It's just like base 10 numbers versus base 2. Base 10 is natural, intuitive, only because you're so used to it. Because it's one of the most odd bases of all. Okay? Well, not most, but it is odd. A penny. What is the next one?
Nickel.
Nickel. Next one. Next one. Next one. And most common ones, so we're not counting on 2, 5, 10, 20, 50. I don't own anything more than 50, so that's it. That's the end of it. Okay. Do we see any regularity? Do we see anything that's even repeating?
Well, they're all like base 5.
No.
No.
Well,
No.
not base 5, but like divisible or multiple. You know, like,
Okay, let's
except for
turn this
1.
up. 5, 2.
If you
What
take
about
out
this one?
if you take out the quarter, it could actually work.
2.5. And then what? 4. 5 again. 2. Well, it should be 2.5. No, we have to go for 2. And then we go for 2.5.
I mean, they're not consistent, but they have something in common.
It's just like saying pi is repeating some kind of random 10 digits over it. It's just a random ordering of 10 digits, right? No, there's no order. There's no pattern in this thing. And yet you can deal with this. So can everybody who works for McDonald's.
I can't for that one.
So why? You'll work for Costco. You don't have to touch money. Credit cards. So anyway, you can deal with this. Base conversion is easier. Why do you think base conversion is easier? Imagine a money system where the denominations are more like this, okay? You have $1 bills, you have $2 bills, you have $4 bills, $8 bills, $16 bills, $32 bills, $64 bills, and that's the highest I will have in my wallet, okay? And then in the opposite side, what do you think we're gonna have as coins? Half, yeah, exactly. So we have half dollars, quarter dollars, and let's say we all go all the way down to $8. That is the money system that we're dealing with. So let's see if we can work with this one, okay? And I'll pick a number that's easy to convert because this 0.78, not easy to do. So we'll pick something that's easy to do. We'll pick a 40, maybe something a little more challenging. 43, and that, okay? How do we do this? Use the least number of bills and coins to make up for $43 and 375 thousandths of a dollar. What do you do? What do you do? Same approach as with just the regular money system, right? You start with the highest number that is less than or equal to the value that you're dealing with.
So we could do 132.
Okay, so let's go ahead and look at, so how many 32s do we need? One. Okay, so one, we take care of the 32, we have how much left? Okay, so 32, we have 11. So we have this much left, right? Let's see, can I work at McDonald's? Yes, okay. Okay, so that number, 11.375 is less than 16, so we know there are no 16s. Is that working? How about $8? $8. We got one, okay, so we take care of that one. So we minus 8, so we have 3.375. So that means there are no 4s, right? We're now down to 2, we got 1, 2, right? So we are now down to 1.375, and so we have 1, 1 as well. Then we move on to the half dollar, right? Do we have any half dollars? Because the remaining portion is 0.375. No half dollars. Okay. Quarter? We got 1. And what about 1/8 of a dollar? Okay, so we got one of these. All right. How many people see a binary number? In fact, this is not just a binary number. This is a binary number with a binary point. We cannot call this a decimal point anymore, can we? Okay? That's base conversion. Give me a value. We go through this process, and then we end up with a base 2 number. But this is easy. This is way easier than other bases. It's way easier than this because there's no division involved. Every single step, there's no division. What did we do instead? Compare and subtract. That's all. No division, no multiplication. Because in the end, we can only either have 0 or 1 of each power of 2. So all you need is just to compare. Is it greater than or equal to? Yes. Okay, there's one of those, subtract it. If the answer is no, skip to the next one. So when we read this one out as a number, it is 101011.011 as a binary number, base 2. Sorry?
It's like imagine the guy at McDonald's giving you that as your total.
Okay, I can see your hesitation because of the number of digits that you have to spell out. Let's convert this to hexadecimal. We go from base 2 to base What is hexadecimal?
16.
Base 16. Hexa is 6, decimal is 10, so when you add 6 to 10, you get base 16, right? We just got through one base conversion. Now we have to go through another base conversion. But this one is easy, I promise. But that's what I say about everything. But this one really is actually easy. Okay, base 2, base 16. Does that work? 0 is 0. Would that work? Next one? What is the next one? 1 0. Okay. The base 2 is 2 in base 16. 3, 4, 5. Well, this is a table. This is a lookup table. There's not supposed to be a pattern. 0 1 1 0, 0 1 1 1, 1 0 0 0, 1 0 0 1, 1 0 1 0. Lowercase a or uppercase a, because we have to borrow from the alphabet to make up for representation in base 16. Okay. 1 0 1 1 is B. 1 1 0 0 is C. 1 1 0 1 is D. 1 1 1 0 is E. And then finally 1 1 1 1 is F. Okay? The table. How do we apply this table? This table only works when you group bits by groups of 4. Okay? So what we need to do is to look at this number here and say, well, can we pad enough zeros so it looks like it has multiples of 4 digits? Let's see. 4 digits. Good. We just have to pad 2 zeros here. Does that work? Because you can pad as many zeros to the left-hand side of the whole number and not change the value that you are representing. Yep.
But you're gonna have to add. How about the end though?
You have to pad on this side, and then the other side you have to pad as well. Is it okay for me to pad a 0 here? Does it change the actual value represented?
Not scientifically, no.
On a floating
No.
point?
No. Okay, so we just want to pad it so that we have multiples of 4, right? So now we have another 4 digits here. How do we apply that table that we just talked about? It's called a lookup table, and how do you use a lookup table? You look it up, right? 0 0 1 0. So even if you don't know anything about binary number, you can still use a lookup table because you're just looking up the binary pattern of 0 0 1 0, which turns out to be 2, right? 1 0 1 1 as a binary pattern. You don't even have to go through the calculation, just look it up. It's a B. Okay? 0 1 1 0. You just look up the table. It is 6. So as a hexadecimal number, the same quantity, 43.375 in base 10, is 2B.6 in hexadecimal. Don't you think we should all be using base 16? But the base conversion this time did not even involve comparison, did not even involve subtraction, right? Because what do you think is the special thing about what is special between 2 and 16 as opposed to 2 and 10? 16 is a power of 2. That is exactly it. And that's why we have to pad until we have blocks of 4 bits. Because every 4 bit is 1 hexadecimal digit. And that conversion is easy because it's just a table lookup. It goes the opposite direction as well. If I give you a hexadecimal number, you just have to look at the table in the opposite direction. Then you get a binary number. Is that okay? Is everybody getting all this stuff here about base conversion? Okay. Now there is octal number as well, because 8 is also a power of 2, and it has certain properties like this. But it is falling out of favor because how many bits is in the byte? Well, we're talking about computer science here, not actually byting. Okay? 8. There are 8 bits to 1 byte. So if you are to use base 16 representation, how many base 16 digits do you need to represent 1 byte? 2. What about octal digits? Each octal digit takes care of 3 bits. So how many do you need to represent 1 byte? 2 point something, right? You need 3, but the most significant digit can only go up to a certain point because you don't need the entire digit. So that's why hexadecimal number is so nice, because from looking at the hexadecimal number, you can very easily and visually see the boundary between bytes. Okay, so that's why when you look at when you watch sci-fis, people are dealing with computers, they spew out all kinds of hexadecimal numbers, and that's why they spew out hexadecimal number, because they are easier to understand. They are more compact compared to binary numbers, and yet they still have the property of staying close to the transistor state, being zeros and ones. Okay. Are there any questions? Or are you guys just about to poop out? Okay, so one more thing. This is a reading material. I hid the other and only displayed this one because I just wrote it. Okay, so I want you guys to read this one. It looks like a quiz because I tried to make it more interactive. So you read a section, it will ask you a question, and you have to answer it, move on to the next page, and stuff like that. It is not actually graded. Okay, so if you not answer anything and just move on to the next one, it's just as good. But I do want you to kind of think about the question at the end of each page, just to see if you understand the concept. Okay, that's basically what it is. So it's really just reading material. It's the reading material that was previously in binary numbers, addition and subtraction, and also half adding and full adding. Okay, so it's combining those two hidden items that you cannot see anymore into this kind of newer material. I can give you a preview of what it looks like, just in case you guys have any questions about it. So you can click it. It will say, well, in my case, it says your preview, but in your case, it will be kind of more of an actual quiz. So it has one part that you have to read through, and each one has a question at the end. You just answer the question, or if you choose not to answer, you can just click next to the next question. And once again, how many points you score in this quote-unquote quiz does not really add up to your score at the end of the semester. Okay, this is really just reading material. I just try to make it more interactive, that's all. Okay, but this is your assignment. This is your reading assignment, which means even though it is not counting to your grade, I am counting on you to have read this by next Tuesday, so I will be talking about these concepts on Tuesday. Okay? Any questions? So your current homework is still just that homework, where you have to download the Linux virtual machine, do a few things on it, and then create a file, upload the file back into Moodle. That's the only homework assignment at this point. Plus, just the reading assignment. All right. So did you guys learn something new today? Yeah. All stuff that I already know. And I still don't know why I have to learn this.